Let's start this afternoon session. Professor Bromberg from University of Utah, he would be talking about Schwarzian derivatives and Epstein surfaces.
Okay, thanks for coming back. So I was going over my talk and I was thinking that what I'm about to do now is going to do as the punchline, but now I'm worried I won't make it to the punchline looking over everything I wrote. So I'm going to start with the punchline and then we'll work our way backwards. So let's just remember what we were talking about the other day. So if we have a map from the upper half space to, say, the Riemann sphere, and it's locally univalent, then we defined this map from the upper half plane to the Lie group KSL2C, which is the automorphism group of the Riemann sphere. And then I talked about how you could extend this map to a map of hyperbolic space. So I want to talk about that again. So I wanted to use this I want to define a map. Oh, let me state the theorem that I want to prove. So, and then we also, out of this construction, we built this thing called the Schwarzian derivative. SF, which is a holomorphic function defined on the upper half plane. If there was some equivariance here, we'd really want to think about this as a quadratic differential, which is something maybe I'll come back to. And then we had a norm of the Schwarzian, which was defined with respect to the hyperbolic metric on U. So if rho of U, if this is the line element for the hyperbolic metric, then we wanted to take the area element, so we squared it. And the point is that this norm is invariant under the action of hyperbolic isometries on U. So there is a classical theorem of Nahari. And it says that, so our initial assumption is this map is locally univalent. It's locally injective. So this theorem of Nahari says that if the L infinity norm, so for the L infinity norm, we just take this pointwise norm and we take its sup norm. If the L infinity norm is less than a half, that implies that F is globally univalent. Okay, so injective. Okay, now the classical proof of this is not particularly hard. Certainly the proof that I'm going to present is much more difficult. But my point is I want to introduce some methods that relate to three-dimensional hyperbolic geometry, which I think are useful for other things. So this is sort of a proof of concept of why what I'm about to do for most of the day is a useful thing to do. So let me give the rough idea of how you could prove this. And to do that, what I'm going to do is I'm going to extend this map to a map from to hyperbolic 3 space. So I'm going to define a map from all of hyperbolic 3 space to itself. And that extends continuously to the upper half plane, which sits in the Riemann sphere, which is the boundary of H3. Okay? Well, once I define the map, what the punchline is going to be is that with the assumption that the Schwarzian is less than 1/2, this map is actually going to be a bi-Lipschitz map from H3 to itself. And then there is a classical, I don't know, classical is the right word to use here, but if you have a bi-Lipschitz map of H3 to itself, it extends to a homeomorphism of the boundary of H3 to itself. Now, this construction that I'm going to do, which I'll say in a second, it's always going to extend continuously to the upper half plane. Okay? But we don't know we don't know in general that it will extend continuously to the whole Riemann sphere. So the point here is we're going to get a map that's going to extend continuously to a homeomorphism in the whole Riemann sphere. Well, then it certainly had to be injective on U. And so what is the map? So now, how do we define U? So I drew this picture the other day, and hopefully I'll do a better job this time. So what's the point here? So let's draw the upper half space model for H3. Over on the right here, so the boundary, so I think of this rectangle I draw here, that's the complex plane. So I want to think of H3 as being identified with the complex plane across the positive real numbers. And here's the picture of the complex plane. Here's the upper half plane. And all I'm going to do is if I pick an arbitrary point P, maybe I'm going to draw it over here. If I pick an arbitrary point P in H3, well, what I'm going to do is I'm going to take well, first of all, I'm going to fix the plane above the real axis. So this is a copy of, this is the real axis. This is a copy of H2. And I drew this picture the other day. So we're going to take the unique geodesic. So this is the unique geodesic through P that's orthogonal to this plane. It lands in a point Z. And we're going to define f of P to be equal to, well, I'm going to take this Mobius transformation. So for every point in the upper half plane, I have a Mobius transformation. I think of this Mobius transformation as a hyperbolic isometry. And I hit this, I apply this hyperbolic isometry to P, and that defines the map. Okay, and then the proof of Nahari, of this Nahari theorem, is the following. So this will be what we'll try and show today, and this is that F is a bi-Lipschitz diffeomorphism of H3 if the Schwarzian has L infinity norm less than 1/2. Okay. So this is our goal. So this proves Nahari because if you have a bi-Lipschitz diffeomorphism H3, it extends continuously to homeomorphism. This map by construction extends continuously to U, to the upper half plane. And if it extends continuously to the whole Riemann sphere, as a homeomorphism in the whole Riemann sphere, when we restrict it to U, it will be injective. Yeah, so F extends continuously just by the construction of it to F on U. All right, so I'm going to start talking about some basic differential geometry in a second. If you don't want to hear that, what you can do to amuse yourself is you can also think of this, we can also define a map F bar from the lower half plane to C hat. And the construction is basically the same. Well, it's actually a little bit easier because you don't even need to think about hyperbolic space. So how can you do this? How can you define this map? So I'm going to define F bar. Well, what I'm going to do is, so this is a point in the lower half plane. So Z bar is a point in the upper half plane. So now this is a Mobius transformation. And now I just apply this Mobius transformation to Z. Okay, so now we have a map of the upper half plane into the Riemann sphere C. Right, so in this picture, we're thinking of the Mobius transformations acting on the Riemann sphere. And over here, we're thinking of the Mobius transformations acting as hyperbolic isometries. Now, if you want to amuse yourself, you can calculate the Beltrami differential of this map. Okay. And you can see that the Beltrami differential of this map is less than 1 exactly when the pointwise norm of the Schwarzian at z bar is less than 1/2. And it's not, if you write down, I wrote down the Taylor series expansion of this osculating Mobius transformation function. You just need to differentiate that formula. And if you're like me, you'll find it very satisfying that you get the right answer. It also, once you do it correctly, you'll see that it's very easy, but then it's one of those things like in computer science, where once you get the right answer, it's very easy to check that it's correct, but it's like nearly impossible to actually do the computation. But yeah, anyhow, you can calculate this Beltrami differential very explicitly. And sort of a little hint is if you can you can convert a quadratic differential into a Beltrami differential. And that's basically what's happening with the Schwarzian here. Okay, so I want to put that aside for now, and now I just want to talk about some geometry of surfaces in just some, I'm going to start off just in some very general situation about you have a n-dimensional manifold immersed in an n+1 dimensional manifold, and just some basic, stuff about isometric immersions and the shape operator, and then we'll get more back into the specific situation that we're interested in. So, some general, at least that's how I labeled it in my notes. All right. So, what's the setup that I want to talk about here? So we have some manifold, and we have some metric on it, and then that metric determines a Riemannian connection. So this is some manifold. This is a Riemannian metric, and then this is the Riemannian connection. Okay. And I want to immerse inside M. So this is an immersion. And let's assume that the dimension of M is just one less than the dimension of M bar. Then the metric induces a metric on M. And it also has some connection. Okay, so this is probably a familiar setup to many of you. So one wants to understand how the geometry of M is related to the geometry of M bar, right? How is the immersed manifold curved inside of M bar? And so what you want to do is you want to compare the connection delta bar to novel bar to the connection for M. All right, so let's let X and Y be vector fields on M, and N, the unit normal in M bar to M. So the XY are lying inside M, and the vector field N is normal to M. Okay, so the way that you measure how M curves inside of M bar is you differentiate the normal vector field M. So there's some standard facts that I'm going to write down. Okay, so the first one is that if we compare, so if I differentiate on M, I'll get a vector field on M. But these vector fields also lie in M bar, so I can also differentiate them on M bar. And the point is that what is the difference between these two things? So this is normal to to M. All right. All right, now let's define the shape operator. Okay, in fact, you can write down a formula comparing these two things. All right, so you can think of this expression as giving us some way of comparing how M is curved inside of M bar. Right? This is the difference between the two connections, right? So as I said, it's normal, so if we take the inner product of the normal vector, we see how much we're curved by comparing how big that normal vector is. And you can check that this is equal So this expression on the left is equal to these two expressions on the right. Well, I put this in front. So we have the shape operator. Okay, that's this thing here. What? Yes. That's yes. Doesn't make any sense otherwise. Okay, so this should make some sense, right? We have this should make some geometric sense. We have some surface immersed inside of a. So okay, I'm going to think about this mostly as a surface sitting inside a three-dimensional manifold, and we're just measuring how the normal vector field rotates around as we move along the surface. And so this is called the shape operator. And so the key point is that B is symmetric. Right, that's what this formula says. And the eigenvalues are principal curvatures. Okay, so this fellow here, this shape operator, it's a bundle isomorphism from the tangent bundle to itself. Okay, so now we can stop pretending that we care about some general situation and get to what we really care about, and that's when we have a surface immersed in H3. So now M bar is just going to be hyperbolic 3 space, and M is a surface. Okay, so in this case, we have two very important equations. The Gauss equation, which says that the determinant of the shape operator, -1, is equal to k, where this is the curvature function of M. So this is the Gaussian curvature of the surface M. Okay, so in particular, if the surface is totally geodesically embedded, then the shape operator will just be 0, the 0 operator. And then what does that mean? That means the intrinsic curvature of the surface is -1, just like you'd expect. We also have the Kodazzi equation. And this, make sure I get this right. Okay, so in my notes, I wrote S for the shape operator. And then as I was going on later, I realized I was going to write one S for the Schwarzian. So there might be some point where I write S for the shape operator, because I realized, because that's what is in my notes. So please let me know if I do that. If I don't do that, it'll be a small miracle. Okay, so these are the two sort of fundamental equations of isometric immersions. Okay, so these equations are extremely important, and they have a converse. So if you look at these two equations, what do we need to talk about these two equations? So B is just some object that lies on the surface. B is just some bundle isomorphism of the tangent bundle to itself. So if I give you a surface and I give you a metric on it, and then I give you some isomorphism of the tangent, endomorphism of the tangent bundle, I can ask if that endomorphism satisfies these two equations. And if it does, then we have a converse statement. So this will be very important later. Okay, so there's the converse. And this says if given a surface, and I'm going to call my surface as omega because, well, I am. Given a surface omega with a metric, and some bundle endomorphism from the tangent bundle to itself that satisfies the Gauss and Gongopadhyay equations, there exist, sorry, forgot one thing. Let's assume simply connected. There exists an isometric immersion into H3, and this is unique up to post-composition with isometries of H3. So if I give you some surface and some Riemannian metric on it, that Riemannian metric comes with a Riemannian connection. And so then I can check if my bundle endomorphism satisfies both the Gauss and the Gongopadhyay equations. And if it does, then our surface isometrically immerses in H3. And that immersion is essentially unique. Okay. So what I'd like to understand is how does the geometry of a surface immersed in H3 change when I flow it in the normal direction? So the geometry of a surface in H3 change when flowed in the normal direction. How does the metric change? How does the shape operator change? And then I look to see what happens as I go to infinity, right? So we draw this picture the other day. So I have some surface, so all my surfaces will really look like lines or curves, and then I start flowing it out. And you can see where the surface is concave, right, the metric is going to contract. When the surface is convex, the metric is going to expand. But the amazing thing that happens in hyperbolic space, if the metric starts out concave, it can vary, as long as it's not too concave, what will happen is it will sort of very quickly become convex, and the whole thing will start to expand. Okay, so how am I going to do this? Well, so I have my surface immersed in hyperbolic space. So what we'll do is we'll lift it to the unit tangent bundle. We'll flow it along the geodesic flow. And then we just need to understand how the geometry of a little bit about the geometry of the geodesic flow. So again, let me do a little bit of setup here. All right, so again, eventually we're just going to restrict to the case when M is hyperbolic space. But again, let's start with some manifold, some connection, symmetric and some connection. And then we have two maps here. Okay, so the first one is just the projection from the tangent bundle to the base. And, well, what happens when we take the preimage of a point here? Well, this, of course, is just the fiber. And on the level of, so if I look at the derivative of this map, well, this is going to be a map from the tangent bundle to the tangent bundle. The tangent bundle of the tangent bundle, sorry. So the kernel of this, what is this going to be? This is going to be naturally isomorphic to the tangent space at V. I mean, this is going to be exactly, sorry, the tangent space of the tangent space. Right? So we have the tangent space of the point, we have the tangent space of M at P. And now we have a vector in this tangent space, and we're taking the tangent space of that. But we're taking the tangent space of a vector space. So this is just canonically isomorphic to the tangent space itself. All right, now I want to define another map. Now this map is only going to be locally defined. So I'm not going to, yeah. So I want to define a map from the tangent bundle to the fiber at P. And this, what I'm going to really care about when this is hyperbolic space in general, this is only going to make sense locally, but let's ignore that point. And so how do I want to define this? So given x in the tangent space at some point q, nu of x is just parallel transport of x to dp of f to the tangent space at P along the geodesic from P to Q. Okay, this is why this is only locally defined. If we were in an arbitrary manifold, then this geodesic wouldn't be unique in general. But if we were in some small neighborhood of P, then it would be. Okay, now here I want to do the same thing. I want to look at the kernel of this map. Okay, so this will, this again is going to be naturally isomorphic to the tangent space at P. Now notice that this map doesn't depend on the metric at all, but this one does, right? So these two, right? So the point is when when I take the kernel of this map, the kernel of the nu, when I project this by pi, this will be an isomorphism, right? So the pi star restricted to this kernel is going to be an isomorphism to the tangent space at P. And so that's how we get this isomorphism right here. Okay, so what this gives us, so if we look at the tangent space of the tangent space, what we've done here is we've given this, this is canonically isomorphic, given the metric to just two copies of the tangent space of the original manifold. And so I want to think of the second one as being the kernel of pi star, of pi, yeah, and the first one as being the kernel of nu. Okay, now if we get what is a vector field on M? So let's let X be a vector field. So if we do this, well, what is a vector field? I mean, this is a section of the bundle, but if you're thinking just in terms of differentiable manifolds, this is just a smooth map from M to the tangent bundle. Okay? And then there's a little lemma here. Okay, so if I take the derivative of this map, right, this is a map from the tangent bundle to the tangent bundle of the tangent bundle. And if I apply this to another vector field, I get the following with respect to this decomposition. So the first coordinate is just, I get y back itself, and the second coordinate, I get the covariant derivative of x in the direction of y. Okay, so why am I doing all this? So the point is, what do I want to do? I have this map, this surface, immersed in hyperbolic space. I'm going to lift it to the unit tangent bundle. How am I going to lift it? Well, that's basically what I'm going to. That lift is just I'm mapping in the normal vector field. So what I'm going to see is when I do this, when I do this map, the first coordinate of this derivative will just be the regular derivative, and the second coordinate will be the shape operator. All right, so given some map, some immersion, we lift. Okay. And then what is this lift, right? This map is exactly, this is the normal vector field. So we're mapping a vector field into the unit tangent bundle here. And so then what we get is that if we take the derivative of this map and we apply it to some vector field, well, what we get is that this is just f star of x and the shape operator of x. Oops, told you I was going to do that. Where B is the shape operator for the immersion. Formulas make sense? Prince Wild looks okay to you? Okay, so what do we want to? So what do I want to do with this? So I have a geodesic flow. And now I can just let f hat of t be equal to post-composition with a geodesic flow. And f of t is just projected back down to the hyperbolic space. Okay, so I'd like to understand, how, as I said, I'd like to understand how the metric, how the metric on the surfaces coming from f of t change as t changes, and I'd also like to see how the shape operators change. So let's give ourselves some more names. So let I sub t. So this is we have the first fundamental form, just the metric on the surface. And S of t is the shape operator. Okay, so how do we calculate how these things change in comparison to the original map? And so the point is there's just a nice expression for them in terms of the shape operator of the original map and the metric for the original map. And to see what that is, we just need to calculate the derivative of this g of t. Okay, so I want to calculate what? Oh, see. Thank you. I knew I would do that. To calculate this derivative. Okay. Now the point is, right, the geodesic flow has nothing to do, I mean, this is a very, very, very concrete thing, right? It has nothing whatsoever to do with the surface. And we can just explicitly write down what this derivative is. So the first thing we want to say, okay, so we had this decomposition of the tangent bundle to the tangent bundle. Now we have the unit tangent bundle. So what happens? So what happens, where was, yeah, so if I restrict this to the unit tangent bundle, what happens is this first term stays the same, but in this second term, we'll only have the part of the tangent space that is, so now our vector, right, our vector v is lying on the unit sphere, and we'll only have the part of the tangent space that's tangent to the unit sphere. Okay? So let's say that a bit more explicitly. So if we're given, so if we're at given some point in the unit tangent bundle, I can let T, P, V orthogonal. This is going to sit inside of the tangent space at M, and this is just going to be the vectors orthogonal to V. And the key point is that when we restrict to the unit tangent bundle, all we have left here in the second coordinate is this orthogonal component. We can also decompose the first component as the part that is in the direction of V and the part that's orthogonal to it. So here we can write so we take the decomposition that we had before, And okay, so the first component, so this is just the part of the tangent space that's pointing in the direction of V. This is the part orthogonal to V. So this is the first term, the first component before, and this is the part of the second component that's left. Okay, so then, well, then we just check. So in these coordinates, we get a very nice picture of what the derivative looks like, and I'm going to write down a matrix. Okay, so this is the derivative. So what do I mean by this? Well, this is a matrix of matrices, I guess is one way you can think about it. This is a matrix of operators. So what this is saying, what does the derivative do? In the direction where we're flowing, the derivative is just basically the identity. Well, this doesn't really make sense, right, because we're going from the tangent space at, say, a point P to the tangent space at a point Q. But so if the geodesic flow takes the point P and the vector V to the point Q and the vector W, there is a canonical isometry from Tp of M to Tq of M given by parallel transport. Okay. So what I'm really doing is first I'm applying parallel transport, and then I'm multiplying. Then I'm applying this matrix. Does this make sense, what this matrix is indicating? Say again? Up here? These are both the same, right? So we had this decomposition of the tangent space to the tangent space. And the first term, I lost the direction where we're flowing in, but not in the second term. In the second term, we lost it, not in the first term. Okay, so now we can just use this. And what do we discover? We discover that if I want to compute the inner product between x and y, well, just applying this formula, I'm going to see that this is the inner product of x plus cosh tx and y plus, wait, not doing that right at all. Okay, somewhere. Right, because how do I take the derivative? So what is f of t is the composition of f hat with g of t. So I'm just applying the chain rule, right? So f hat t star of x. Well, this is this matrix Okay, and so I just multiply this out, and if I want to find out what happens to x, I look at the, just the second term in this column vector. And if I want to find out the shape operator, well, what do I see? So this first formula, so I multiply this through and I get this middle row, and that gives me the first formula. Right, so what about the shape operator? So what I have is that if I look at the bottom row, what I see is that the shape operator applied to this make sure I get this right. Is equal to, this should be an x here. Okay, so just to make this slightly less crazy looking, let's call this A of x, and let's call this fella script B of x. And what we see, this is the okay, all right. So rewriting that. So if I want to find out just what the new shape operator is, I just replace x with A inverse of x, and we get the following formula. So if you diagonalize the matrix, if you diagonalize the shape operators by taking the directions of principal curvature, what you can see is that the principal curvatures, you get a reasonably nice formula for them. So you have two of them. At time t, what do they look like? They're just the initial principal curvature. Okay, and you can check that this behaves exactly like it's you expect it would when your initial surface is, say, a sphere, or another good example is the geodesic plane. And the other thing to notice is what happens as t goes to infinity is that the curvature goes to 1, right? So as you flow out, your surface is going to look more and more like a horosphere. Yeah. Okay, so another thing I'd like to point out here is that when is this new metric positive definite? Ooh, it suddenly got quiet. Nice. When is this new metric positive definite? Exactly when the principal curvatures are not -1. Right? So this is always positive definite. Yeah, you can see there's going to be, so I'm sort of ignoring this point, but I don't, so you can have an immersion into the unit tangent bundle that is nice and smooth, but the map into H3 itself might not be. You can have points where the curvature is actually infinite. And I'm gonna ignore that point. But it doesn't really matter because when you lift it to the unitangent bundle, things will still be smooth. What? Yeah, that's what I'm saying. No, it's not always invertible. Yeah, that's exactly the point. Yeah. So if the principal curvatures are always less than 1, it is always invertible. Yeah, I mean, maybe that's what we're saying here. So if the principal curvatures, if the absolute value of the principal curvatures are less than 1, then this map AT is always invertible. And the surfaces give a smooth, and the surfaces foliate H3. Okay, so what I'd like to do now is I just want to take a limit as t goes to infinity. And what you notice is you just get a very simple formula for the limit. Okay, and the point here is that so I infinity is positive definite if and only if the principal curvatures do not equal -1 anywhere on the surface. Right, so if you have a principal curvature that is -1, in that direction, this inner product will be singular. And you can think about what's happening there. So if you have a horosphere and you start flowing in, your metric is just going to degenerate. Everything is going to sort of converge to a point. Okay, so I don't really want to make any strong assumptions about the surface. I mean, I don't really want to assume that it's embedded. I mean, everything I'm saying applies even when that's not the case. But to think about what's happening, I think it's a little easier to assume that this surface is embedded and that it limits to something nice on the boundary. So let's draw a picture. So here we have our initial surface, and let's just, like I said, assume that it's embedded, and then we're flowing it out. And eventually it's going to start becoming convex. And it's going to limit to some surface on the boundary. So we can let F infinity be a map from so omega at the start is just some differentiable surface. And this is going to be a map into the boundary of hyperbolic space. And the definition is just going to be F infinity of z, which is going to be the limit of the f of t's. Okay, and just to make it easier to think about, let's just assume that this map is injective, globally injective. So I'll put it in parentheses. I mean, we don't really want to do that because what we want to do is, in the end of the day, we want to prove that a map is globally injective. So we better not assume that it is. But just for purposes of thinking about what's going on, let's assume that F infinity is injective. And F infinity of omega is conformally just the upper half plane. Okay, so this is some region now. I mean, I have a map to the Riemann sphere, right? So I can pull back a conformal structure on omega. So it started off, I was just assuming omega had some differentiable structure, but now I can pull back a conformal structure. Let's assume that it's simply connected. So it could be the plane, or it could be the disk, or it could be, I guess, the whole sphere. But let's assume it's the disk. That's the case we're interested in. And now we can replace omega with u. So I've just I've picked my conformal structure so that my map at infinity is a locally univalent map. What would happen if I flowed to negative infinity? Well, then you would just replace the shape operator with the negative of the shape operator. So both of these pluses would be negative. So you can do something that may appear funny to begin with, but we'll see in a second that it makes sense. So I want to define what's called the second fundamental form in infinity. And what I'm going to do is I'm just going to replace one of the pluses with a minus. Oops, that's not what I wanted to write. Okay, so this is some quadratic form, and I can rewrite this. I mean, I can do a little bit of linear algebra if you want to say what this is explicitly. I can write this in terms of the metric at infinity. In particular, there's some so there's some endomorphism of the tangent bundle of U, so that this equals this. This is the B infinity. So this B infinity is the shape operator at infinity. Okay, so let's finally start bringing this back together to what we were discussing before. So here is the following theorem, and let's see if I can spell this name right. Okay, so this is, I think, originally due to Takhtajan and Teo, and maybe sort of a different proof of this due to Krasnov and Schlenker. And it says the following. So if we're really lucky, this metric at infinity, so this metric at infinity is some metric on U. If we're really lucky, this metric will be the hyperbolic metric. And if that's the case, then this shape operator at infinity will be the Schwarzian derivative. Okay? Well, not almost. So let's write it down. So if the metric at infinity is the hyperbolic metric, then the traceless part of E infinity is 2 times the Schwarzian derivative of f infinity. Okay, well, why does this make any sense? So the shape operator infinity, right, this is a bundle endomorphism. This is just some holomorphic function. But remember, you should really think of this as a quadratic differential, right? So what's a quadratic differential? It's a C bilinear map of the complex tangent bundle. Oh, I'm sorry. I want to take the real part of this. Sorry. So this is a okay. So S of S infinity. What is this? This, you can think of this as being, I mean, it naturally is a map from the complex tangent bundle it's C bilinear. Now, what happens when you take the real part of such an object? Okay, well, first of all, this is always this is a one-dimensional over C, so it's always going to be symmetric. And when you take the real part of it, it's going to be traceless. So if I take the real part of the Schwarzian, I get some traceless object. And it's going to turn out to be exactly the traceless part of this shape operator in infinity. Okay, so this is just some linear algebra. What is the trace? Yeah. You can read an early paper of Francois, and everything is just a little bit of linear algebra. That's it. All right. So what is the trace? So there's also the trace also has a nice description, and it's the curvature. Okay. So again, this is another theorem of Krasnov and Schlenker. And it says the following: if I take the trace of this shaper operator in infinity, it's twice the curvature of the metric. It's negative twice the curvature of the metric. So this is like a version of the Gauss equation. And the other thing that's nice about this shape operator infinity is it satisfies the usual Gauss equation. So nabla is the connection at infinity. Okay, so why is this a good thing to have? So we have essentially, and not essentially, we have an algebraic operation going from the metric on the surface in hyperbolic space to the metric going, given the metric on the surface and the shape operator on the surface, I have an algebraic operation that gives me this metric at infinity and the shape operator infinity. And this process is invertible. This process is invertible. So if I know the geometry of one, it tells me the tells me the geometry of the other one. And in particular, yeah, so here, let's write down a little sort of a theorem proposition that is very useful. So I have these objects on the surface in hyperbolic space, and then I have these objects on the surface at infinity. And I can go between one or the other. If you give me one, I can give you what's happening on the other. And the point is, if you give me a metric on the surface and a shape operator on the surface that satisfies the Gauss and Equation equations, then the metric at infinity and the shape operator in infinity will also satisfy the Gauss and Equation equations. And you can go back and forth. If they satisfy that to infinity, then they satisfy that on the surface. So, right, so this is an if and only if statement. So in particular, if you give me a locally univalent map, so if instead of starting with a surface, let's say I'm given a map, I can define B infinity to be equal to twice the real part of the Schwarzian derivative. And then I add to it minus. So I want to do this for the hyperbolic metric. So what's the curvature of the hyperbolic metric? It's -1. So I take -1, 2 times -1 times the identity. And I let that be, this is going to be my shape operator infinity. And then we can check that with this definition, B infinity satisfies the Gauss equation. Now it automatically is going to satisfy the Gauss equation at infinity because, I mean, that's how I set it up, right? This part is traceless, so the trace is exactly 2. And it automatically okay, so now I can apply this theorem, and this produces another metric and another shape operator that satisfies the useful Gauss and Equation equations. And this produces an immersion. But I can do even more than that, right? Because I have the relationship between these metrics is very explicit. Okay, so in particular, maybe just to, what do I do with that thing? So just to give some idea of how explicit this is. So in particular, so let's just assume that we're at some point where the Schwarzian is real and positive. Then in this case, B infinity is just going to be given by Okay, I don't need to take the real part because it's already real. And again, there's just some algebra that you can use, and you can use this to reconstruct B. Somewhere I wrote it down. Let's see if I can find it. Okay. I can't find where I wrote it, so hopefully I get this right. So what's the point here? So the point here is my assumption is that this Schwarzian is less than 1, right? That was my initial assumption when I started talking. We want to assume that this norm of the Schwarzian is less than 1. And let's assume we're at a point where just so we don't have to worry about the metric, where the imaginary part is 0. And that's when the hyperbolic metric is 1. Otherwise, you have to put that into our equation. And that will just make me confused. So if I wrote this down correctly, and I can't find where I have it in my notes, but I do somewhere, what you see is that when this Schwarzian is less than 1, both of these curvatures are between -1 and 1. So when this Schwarzian is 1, that's exactly the case when we have this surface when we flow in the normal direction, it will foliate all of hyperbolic space. And the point, sort of the punchline, the way we get the proof of this Nahari theorem is, let's draw our initial picture. Okay, so what is the image? So I had this map F that I defined, an hour and 14 minutes ago. And I had this, so I got the image of the surface under F will be some surface. And that surface is going to be exactly the surface that I'm describing here, that I get through this construction. And now if I take the plane, if I move some distance t from my original plane, I'll get another surface. Okay? And the way I get that other surface is I do the same thing, except instead of taking the hyperbolic metric, I rescale the hyperbolic metric. And the point here is that I have this very simple way of going from the metric at infinity to the metric in hyperbolic space, and I can use that to show that this map is by Lipschitz. Right, so you can write down, so in particular, I have a formula, there's a simple formula writing down what the metric at infinity is in terms of the metric on the surface, but you can also go the other way. You have essentially the same formula where you swap the roles of the I and the infinity and the non-infinity part. Okay. And you can use that to see that, so for example, you can use that to see that the map from the hyperbolic plane into hyperbolic space is by Lipschitz. With good control of the by-Lipschitz constant. And you can do that to study this whole map out. Okay, I'll stop there. Oh my gosh, I never said the word Epstein surface. So what these surfaces are, these were originally studied by Epstein, and he constructed them in a different way. But these things, geez, that's terrible. These things are really originally due to Charlie Epstein. And those are the Epstein surfaces.
Any questions? Otherwise, let's thank the speaker again.